Okay. Okay, how is our computer doing? Computer is not struggling too much. Okay. Homeworks, questions, anything? Sorry? Yes.
So for a range tree, or not a range tree, an R tree, do we have to cluster basic blocks that are on the same level? Or?
So you arrange it into pairs. You start when every segment. It's a binary R tree. It's not a high degree R tree that I discussed in class. I mentioned that R tree, sometimes we want to have every node have plenty and plenty of children just because then we can better put it in the disk.
Yeah,
but that on the binary.
Segments?
Yes.
Yeah, or 3, that's fine.
So I'll encapsulate each one of them into its bounding box. Kind of bounding box.
Just do a bounding box for the left too,
I could.
and then have a bounding box for that one that you just made and the third one.
So that would be the next level if I'm doing. It's a very easy question, to be honest.
So no, but could you do so those two left as one bounding box, and then the third one together.
So here my tree will consist of these two, and these two.
For that tree, but could you do another tree?
That the clustering will be this and this, absolutely. Because.
So could
But.
So could you have say you have 4 segments? So you have a bounding box for this one here, bounding box for this one here, for all those. Could you then do bounding box for these, and a bounding box for these?
Usually not. If I want to keep it logarithmic height, I'll sample pairs. And now, if you start to add and delete segments or segments are moving, then it's different opera. But usually you'll say, I cluster it, so I'll make sure that the height is exactly log 2 of n. Okay. But
so this would be a bad clustering?
Sorry?
This would be kind of a bad clustering then?
In this example, that's a good cluster, because here, this will be a nice cluster, because if I have a query point over here, hopefully everybody is this a good cluster or a bad cluster? And I argue that for this particular input, it's a pretty good cluster, because if I have a query point, I'll go to the root that knows what is a bounding box of all the segments. I figure out that the query point is in the region of the root. Now I'll check, is this in the region of the left side? No. region of the right side? Yes. So my search path will go all the way until I'm actually here, and then I'll check for this very example where I'm just between the bounding boxes. So,
But for this one, you kind of back to the check.
right. And for the same segments, it's not hard. To see that for the same 4 segments, I can very stupidly find a different clustering that will mean that for the same query point, I need to visit a lot of nodes. Even though it's logarithmic, I'll figure out that there are nodes outside my bounding boxes only at the very latest stages. Why? Because I was not clever enough to, so I have a lot of empty room in every bounding box. Every bounding box contains the segments plus tons of empty room, and the query point might fall on this empty room. And of course, there is a lot of overlapping between the bounding boxes. Now, why would somebody do such a stupid thing for these segments? No, but if the segments are 3-dimensional objects, not necessarily convex, and the segments are more strangely arranged, then suddenly this question of how to cluster becomes quite puzzling. And there is no, as far as I know, there is no great theory behind it that says that's a shape that you need to do, and then you're doing fine. I know about a bunch of papers that tries to say, you know what, instead of bounding axis parallel bounding boxes that takes a lot of area with a lot of empty space, I'll try to encapsulate it. Again, it's 3-dimensional object, and they might have, it's a bunch of cars, so I'll try to find an ellipse or find a sphere between them. Maybe I have less empty room, and so on. Any geometric shape that it takes me constant time to check if a query point intersects it, if it's inside the region, and so on. So there are works about it. There is no correct way, as far as I know, that says that's the only way for the cluster. But so obviously, I want lots of locality. I don't want to leave a lot of free room in my objects where I can have a query point that doesn't fall on any of the segments, but I'll discover that it's not on any of the segments only when after I visited almost everybody in the tree. And if I'm asking for lower bound, remember that it doesn't mean that I visit each and every leaf. I visited linear number. Don't remember the exact wording, but I can visit many nodes of the tree without ever visiting the leaves themselves. So
if you, because it's still logarithmic, right? It was omega n.
the logarithmic comes when I visit either this part or this part. But that happens because in this nice example, there is no point that lies in both of them. Let's say that I'm asking instead, who are the segments that intersect my query segments? I'm going to put somebody here, who are the points that intersect? Or I'm still doing a query point, but my original segments are not so nicely aligned in the x-axis, and I need to cluster this plus a lot of other segments with this plus a lot of other segments. And the general scenario is that bounding boxes are not disjoint. I'm quite lucky when they are. I'd prefer to build them when they are not, when they are as disjoint as possible. And so maybe axis parallel bounding boxes are not the optimal shape. But especially if you live in higher dimension, and then it's just a needle that takes, when I take the bounding box, covers the whole room, and I can shrink the bounding box to another geometric shape. So, yeah, there is. Yeah. Other questions? Okay. Plan for today, we will discuss the building the planar map after vertical decomposition. Remember, the overall exercise is I want to partition the plan into trapezoids. That was easy. And I want a data structure that was much harder, so that I'll give you a query point, and you'll tell me at which cell of my trapezoid, which trapezoid contains my query point. And I want an answer in logarithmic time. That is, I build a Voronoi diagram, for example, of trillion points, everybody in the state. I look at the query point, who is a person that is the nearest right now. That would be an application, like a planar map of Voronoi diagram, and then my input segments are just the edges of the Voronoi diagram. Like, I don't really take advantage of the fact that the cells consist of larger faces. I'll just treat each segment individually. So a plan for today, wrap it up. Mumble without definitely discuss the algorithm. Mumble about the expected time of the algorithm with a bit hand wave. And then we are actually moving to graphics. We are going to talk about algorithms for rendering geometric scene, large geometric scene. We'll mention the limits of why GPU are not the ultimate answer. And then we'll talk about binary space partitions, which, by the way, we have seen a few binary space partitions, like quad trees. Just think about them as every node has two children that has two children, or KD trees, but you can do better if your purposes are to find for a viewer what are the objects that this viewer, this player, sees out of a computer game. You have a big scene and a viewer that just landed right here. What does the viewer see? And that will imply that I want to know what objects are very close to the user, what objects are further away, what objects are further away. And I definitely don't want to know which object occludes partially or completely other objects. So we'll talk about the painter algorithm and about algorithm for constructing another type of binary space partition, BSP, that does better for graphic application. But before that, we need to wrap up the segments issue. So input, as I mentioned, and we think about the vertical decomposition. Just to remind you, every endpoint of a segment shoot away up, shoot away down until you hit another segment, creating one trapezoid, shoot away up, creating another trapezoid. And out of all these segments, all these trapezoid, we want to build a data structure So we want a data structure that in order log n, I'll give you a query point, one of many, many query points that I'll give you, and you'll tell me what out of all the n trapezoids, order n trapezoids, which one of them contains my query point. And the data structure that we discussed last class was very, very simple, very easy to use, once I'll find it. We said we divided our tree into X node, where we just ask, is my query point to the left or to the right of the X node? And the Y node, not symmetric with the X node, that says, is my query point above or below a segment? And segments are not necessarily vertical, but I can still answer. Are you above the line containing the segment, or are you below the line containing the segment? And you're breaking ties by saying if you're just on the segment, then formally you're below it or something. And once we have this scenarios, and we played with this example. I'm giving you your query point. You are going to this data structure, which is not a tree, a DAG, talked about it, directed acyclic graph. I mean, no cycles, directed, only going downward, connected. Start from the root. The root says my query point is to the right of P1. By the way, in this animation, the creator, it's slides that are exchanging hands. I got them from Josh got them from downroot, and I think that it goes back, the creation of this slide goes back a few generations. So here above will be to the left, but right and left are still left child and right child. So Q is to the root is on X node. I'm to the right of the root. My query point is to the right of the value in the root, going to Q1. My query point is to the left of Q1. Q1, I'm to the left, going to the left, and yada yada. And go up, and at some point, asking, is my query point, that was an exciting moment, is my query point above or below S2? That was exactly the decision, am I in D or am I in F? And F was a good example because to F, I can reach via different paths, which makes sense, right? I mean, it would have been very strange if I couldn't reach through different paths, given that it's the splitting are not a split by the X. A split by the X value doesn't really split the image into left and right, because there are regions like F that if I split by P1 is not a good example. If I split by Q1, the part of this trapezoid is on the left of Q1, part of the trapezoid is to the right of Q1. So it's not surprising that there are two paths that reaches F. That is, once I declared Q1 to be part of the tree, I did not split anything that is above or below Q1. So far, so good? OK, let's talk about the algorithm to build the data structure. And it's a very, very clever algorithm, to my taste. I'm biased. And because the data structure that we are going to use during the algorithm is exactly the data structure that is the output of the algorithm. It was a convoluted sentence. I'm going to use the data structure to build the data structure. Maybe. Does this sentence make sense? The same data structure that I'm going to use is used during the algorithm. I'm drawing it during the algorithm. But what do I mean by it? I am inserting the segments one by one, as usual, and as usual, at a random order. At every moment, I have the data structure for point location, the one that is written on the left side of the whiteboard. I have this data structure, just a zoom check, not zoom, just a So my issue is that I'm going to add one more segment to the already existing data structure. And this one new segment that I'm going to add will change the planar map and will change the trapezoidal map, and also will change the data structure itself. But to start with, when you'll give me this segment as a SI segment that I'm just adding, I need to ask, where is this segment in the whole maps that I created so far among all the previously added segments? So to start with, I'll find where is the left endpoint of the segment. Use a data structure created so far. Use the data structure that created for S1 dot 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 Si minus 1 to find the trapezoid containing the left endpoint of Si, data structure of all the way up to the last segment that was inserted, Si minus 1, and now Si is inserted. Find where it is. There is a trapezoidal that contains it. Now, remember this point. What are the neighbors of a trapezoid in this structure? Segments don't cross each other. Don't forget it. So here is one of the trapezoids. One of the segments, a wall of the left part of a trapezoid. How is this wall generated? Maybe it was generated because of so this is delta. Here is the left side of delta. And how did I generate this wall? A few chances. Maybe there is an endpoint of a segment right here, and then this wall go all the way from left and right. That if this endpoint is an endpoint of Sj, some of the previous segments. Just to convince you about this case. In this case, delta has just one wall to its left, one neighbor to its left. Whomever lives here, this other trapezoid that lives right here, is the left neighbor of delta. What's the quote-unquote complicated case? That delta has actually, that this wall was because an endpoint of SL over here. That's how I created this wall. So possibly delta has two neighbors from its left. Delta prime and delta double prime. But it cannot be, under general position, more than two on my left. Agree general position, no two points will have the same x coordinate. Unless, of course, they have a common vertex, they are all meeting there, but that's somehow an easy question. If they are separate, they have different x coordinates. We'll see a cute trick at the end that will relax the general position and will guarantee that I don't have two separate segments that don't meet each other in the left endpoint, but they don't have the same endpoint in the same x value. They are not, so a trapezoid just have one left endpoint. Back to our scenario. If that's a segment that I'm adding, it's inside question. If that's a left endpoint that I was just added, I found the trapezoid that contains it, and what do I do? What happens to this old trapezoid that contains my old segment? It is just split into a few new trapezoids. Right? It just split into 1, 2, 3, 4 trapezoids according to this guy. So I'll just create these 4 trapezoids. And now it looks like I need to delete something from my data structure so far. It's an illusion. The data structure doesn't believe in deletion at all. What will it say? The data structure will say, oh, delta, the big trapezoid that contains everything, before I added this guy, I'm still not in the dotted guy. Before I added this guy, there was one leaf that contains this new segment. I'm speaking too much. Let's do it. So I had here is delta in red, one single nice trapezoid. And in my data structure, even though it's not a tree, this trapezoid, let's call it F, was unique, was a single node. F is not going to be executed because there is now a new segment that crosses it. instead, F stops being a leaf in this DAG. Hopefully, you all understand what I mean by a leaf, even though it's not a tree. Leaf, somebody that doesn't have any children, stop being a leaf in this tree, and instead, I'll assign to delta the 4 trapezoids that are now becoming its children, right? I'll put two X nodes in the, if I'm adding P and Q, then I'll have P as a, that if I'm to the left of P, then I'm inside delta 1. Then I'm inside delta 1. Need colors. If I'm on the right of Q, then I'm inside delta 4. And now I have from this node and this node, these are two X nodes. What about these two guys? Well, it can be two options, but it could be the purple trapezoid over here, which happens if you are below SI, the segment that I just added. If I'm below this guy, then I'm inside delta 2 in this picture. And if I'm above SI, sorry, from P, I need to go to compare yourself into delta I. Okay, I think that it's quite speak for itself. From now, I'll ask, are you above SI, which will tell you if you are inside delta in the image, or in my figure, it will be inside delta 2. And above the segment, I'm inside. Do I have a new color? Should have blue somewhere. I'm inside delta, what did we have? Delta 4, delta 3. I'm inside delta 3, and similarly, you will ask from SI to neighbors. Over here to either delta 2 or delta 3. Yeah?
So the green Q doesn't go to the purple?
If I'm to the right of Q, then I'm inside delta 4. Then I don't care about where the segment is.
Then you would that still be the same SI node?
If I'm between P and Q xy, if I merge these two nodes, I think that I can merge it. But I mean, either way, if I'm already know that I'm inside the slab, and because I went all the way from the root of the tree all the way until I'm inside the big red trapezoid, now I'm asking among the sub-trapezoids. Out of the 4 of them, in which one am I? There is some technical difficulty, and I think that it's quite obvious how I continue, and I will never ask if this is the correct way. Hopefully everybody understands from it, and everybody understands that what I did is, in all these cases, now they are all children of F. And I don't care one bit if all were children of F, pick F and add this little tree like this tiny dog as children of F. That was an easy case. Should I clean it up? Is this clear? I mean, it's a very ugly figure, but okay. Since nobody screams, I'll assume that you're good with this, at least in the level of that. If I'll ask you to figure out the details over here. it will be clear. The interesting case is, of course, if I did not say at any point that I pick the segments based on length or being inside other segments. The order that I increase the segments is random, and every permutation is equally likely. You all remember it, hopefully, from our very first classes. Every time, same tricks that I used in linear programming. I want to create random permutation. I put all the segments in an array. I have an array with all my segments. I pick one of them, I at random. That will be my first one. Replace it with the last element. And now I pick a random number between 1 and n minus 1. And that would be my next element. Put it in the second place all the way until you're done. And then every permutation is equally likely. Each one of the n factorial. Each one of the elements is equally likely to be the first or equally likely to be the last. So I insert the segment in some random permutation, which implies now that I'm inserting Si. I found, just as before, where is the left endpoint of Si. And now things start to be complicated because when I added this segment, it was nicely compacted inside an old single trapezoid, right? So the only change that I had to do is to take one leaf, one trapezoid, and make it into 4 new trapezoids. Here, life are quite different because now this new segment starts to wander, and that's exactly what I'm doing. I'm looking at who is its 1 or 2, and the segment delta 0 knows who is its neighbor from the right. And Si still didn't finish, so I'll keep track into several other trapezoids until it finally terminates. In terms of the data structure, there are quite a lot of changes that I need to do. At the end of last meeting, we discussed that there could be n square changes altogether, and each new segment can stab each old trapezoid pretty much. Right? That we had n square many changes. People, do you remember this example? Well, if I'll ask you to generate it, you remember why? We start when R, this big rectangle that encapsulates everything, is one big trapezoid by itself. Here I'll add, and now I'll add n short segments. S1 dot dot dot, let's call it Sn for not messing up with more complicated segments. So far I didn't create too much changes. Every new trapezoid just changed. Created 4 new trapezoid, maybe less. And now I start to really to make life harder for the algorithm. How? I'll start to add segments where each new segment will create many, many changes. How would they do it? Hopefully you all remember. Here are the walls of the trapezoid that I have from the tiny segments. Not really visible, but and I'll add, let's call it S1 prime to distinguish it from all these guys. And it changes almost all the trapezoids that I had so far. Created linear walk. And when I walked from one trapezoid to the next, I had to spend linear time. So what? We want a linear n log n time algorithm for the whole construction. So just adding one S1 prime is still not my punchline. But next I'll add S2 prime that crosses all the n trapezoids that are still alive. And S3 that crosses of the trapezoid so far, etc., now has to meet all this big cluster of trapezoid and so on. So worst case, like in linear programming, if you find a bad permutation, you have bad karma today. You'll spend a lot of time on the algorithm. And worse, your data structures that we are so carefully designing here that's supposed to guarantee log n query time is useless. I might as well, for a query point, check every trapezoid if it contains it, because if you think about the depth of the tree, it will have n nodes, but the longest path in the tree that you are generating might have linear space. Remember, we never delete anything and we never balance. Our only hope is that I will not, when I think about a trapezoid that has now sub-children, sub-trapezoids that have sub-children of its own, in the data structure that this family tree that I'm growing, it's not a family tree, it's ask for some jokes that will be completely inappropriate. These structures that we are creating will be very bad. Will have height of log n, no matter what your query point. If this is a lower bound that I'm getting, maybe. So really, our hope is that the order will save us. But just to nail the data structure. So what happens to all the trapezoids that you are going through when SI is added? There is no escape from it. You are walking through each one of the trapezoids. And you're generating, but here is a cute point. You're generating from each one of the old trapezoids now a new trapezoid that has SI as a ceiling. As a ceiling, yes. But let's pay attention to this example, for example. So the order that I inserted this segment was S1 prime was a top one, S2 and S3 was not in the game yet, then S2, then S3, and each one crosses all the other trapezoids. Let's think about a different order. Let's say that S3 now becoming the new S1. All these small guys are still in the game. I'm not playing with them in this example. S1 in the game, that was a first long segment that I added. And now I'm adding S2. What are the trapezoids that S2 crosses? Does S2 crosses all these trapezoids that I had from all the small segments? Remember, what are the green rays that I'm shooting? I'm shooting a green ray, but they stop the moment that they hit any of the segments. If S1 was the first one that was inserted, and then I'm adding S2, then all these small green rays that I just showed you doesn't bug S2 one bit. And barely bugs S3 that I'll add next. Rays are stopping, right? So let's think about all these new ways that I'm generating. Well, I do need to generate from each one new child, but essentially that's it. But we discussed the case of adding this guy and updating this structure. So I forgot about the existing slide for it. And now when we are adding SI, I think that the figure pretty much discussed it. Let's look at the trapezoid before the dotted segment was added, SI was added. This was a vertex, I created a ray up of it. This was a vertex, created a ray. These are my old trapezoid before SI is added. I'm finding SI, this guy, it's a new one. What happened to each one of the old trapezoids, say delta 2. Delta 2 still exists in the name of as. Now it has a new name. It's called D. It's updated in the sense that it has a new ceiling, which is SI. And what used to be this part below SI, we don't care about it. It doesn't exist anymore. As I'm walking through the segments, I can check for each one of them. Was it created from an event above SI? Was it created from an event below SI? So as SI went this way, that is this way, that crossed SI, ends now at SI and below it because it was created from a vertex below. This way is ended above, defining a segment for my left. So by keeping track of what is my left, what is my right, what is above me, what is below me from each event it is, I can now start to merge trapezoids where I see none of these ways defines everything until I hit the endpoint of the segments. So this will be my new trapezoids above, and this will be my new trapezoids below, and they're becoming children of whom? They are becoming the children of these trapezoids. And what is left to do is just to realize that the trapezoids all from below, as I'm walking for a while, and I don't see any events, then it's the same trapezoid, so it will discuss only one vertex. It will create only one vertex per trapezoid. Remember, number of trapezoids that are really alive is exactly the number of leaves. A leaf is a trapezoid that exists at the moment. When we are adding more segments, then leaves will grow, descendants below them. Good? To the level of, no? Too high level? It was.
Can you go back a few slides? The one that with the orange, the yellow arrows? Yeah, this one. I didn't understand how that it says that it's not a tree, but like how does it like constructed from that?
So
It says from start from Q1, but why it goes to Q1?
let's think. I added S1. So when I start, S2 doesn't exist. So once S1 was there, I had one trapezoid that is the big one that is now split into 4. Yeah. I don't actually keep a node from it. I'll start splitting from P1 itself as a left node because I created a trapezoid from the right. I'm not arguing that that's the only tree that I could have created. But an option would be you have your trapezoid from the left. Fine, that's the left of the endpoint. That's one of the children of the old trapezoid that was R completely. Next, I'm just inserting this trapezoid, so it created 4 guys, period. So S1 is not very interesting. Next, I am inserting S2. Where is S2 in my whole data structure? It takes me all the way into what used to be the trapezoid here. This this wall was going all the way. Find where is P2 among the 4 trapezoids that exist before. You find it. That will correspond to data structure that ask. I had my 4 trapezoids. Maybe I'm speaking too much. Let's run an example. S1, and when S1 was created, I had a delta 1, delta 2, delta 3, delta 4. And my data structure might have been that was a P1, and P2, and my data structure said if you're from the left of P1, you're definitely inside delta 1, that nothing bad is going to happen to delta 1, also known as A. If I'm to the right of P1, and I'm also to the right of right of P2.
It says Q1 on the, but you use a different letter.
P1 and Q1. P1 and Q1. Yeah, so if you're, thank you. If you're from the right of P1 and also from the right of Q1, then before the data structure was created, I'm inside delta 4. That is going to go through changes as S2 will be inserted. Delta 1 is going to stay healthy, but the other trapezoids are going, some of them are going to change. And how are we continuing? That was Q1. And from, if I'm to the left of, between P1 and Q1, I'm right here, then I don't know where I am, even if S1 is there. At this point, I need to check, am I above or below S1?
Also, that left branch could also be a right branch of a delta 1. Is that right?
At this moment,
Well, no. So, what was that? Is that delta 1? The left branch over there for Q1, the left branch of Q1?
delta 1, the left branch of Q1.
Yeah,
Then I don't know yet. Then
could that
wait.
be also on the,
No, because I already know I reached here, because I'm to the right of P1. I always start from the left to the right. I start from the left endpoint. And I don't have vertical segments because general position. OK. Next, I'm inserting S2. S2 is inserted, find it, it's inside delta 1, which I did not write exactly. What did we say? If I'm in S, wait, I didn't finish the data structure when S1 was there. So if S1, if you're above S1, above here is to the left, above, then you're inside B. Above. Then you're inside B. If you're below S1, to the right from this strange reason, maybe you read my post today, if you're below S1, you were in delta 3 that is going to vanish very soon. So that's the data structure, if I'm not wrong, when before S2 exists. Now I find S2, I find it inside delta 3. So delta 3 will vanish very soon. And as I'm walking below, I realize that I just created, let's switch to different color. The left endpoint, P2 created C. And as I'm tracing it, I realize that this ray will end, needs to vanish from the part over here because it's created by an event above S2. So S2 shields the region below it from this ray at this point. So this will vanish. And I don't see any event below me until I reach the right endpoint. which in terms, I realize that the right endpoint is inside delta 4. But this trapezoid on the right side, I don't need a near point location. I reach to it because I reach a left endpoint, and then I spend quite time in walking, crossing a lot of segments, but they are all going to be vanished. And as we'll see, I actually need to visit very few segments if the god of probability likes me. Okay, these walls vanishes, and that's become a new trapezoid from below. That is, I had two trapezoids here that I had these two trapezoids that below me are becoming one new trapezoid, and above me I realize. I think that you see where it's going. Okay. So how much work do I spend to insert a new segment? And by the way, that's an algorithm that was implemented and is very, very practical and very simple to actually implement multiple times. General exercise and exists in various libraries and indeed works very fast in practice. So what's the time per inserting a segment? It's order of log n for the query. Query point on left endpoint. It's order of log n plus ki, where ki is a number of new trapezoids. New trapezoid, which is also equal to the, up to a constant, which is also equal to the number of old trapezoids crossed by Si. Like a new segment barely creates new trapezoid. It creates one trapezoid from the left, one trapezoid from the right. Si created one trapezoid from the left, one trapezoid from the right, and the other trapezoids that it touches are just modified somehow. They are losing either their bottom or the loft or the top, but definitely we can merge them. So the only key question, and that's a new and brilliant idea, is that how can I bound this number of trapezoids that I'm going to cross? And that's where we need Euler. Because Euler tells us if it's a planar map, you have n segments, then you have n trapezoids, order n. You're right, order n. If you have n, 2n vertices in your map, assuming that you are doing the line strips, that was the exercise that I explained to myself why it's linear. I build a trapezoidal map, not as an algorithm, as an exercise. Mental exercise, I build the whole trapezoidal map by doing a line strip, and from every event, shoot a ray up, shoot a ray down until you hit the other two segments from above and below. How many events do I have? N log n. How many trapezoids can I build? Sorry, how many events do I have? N. One per, I spend n log n per order log n per each event, but I have only 2n endpoints, and per each event I change constant amount. How many trapezoids can I create if I just have n events, and every event creates 2 rays? How many rays can I generate? 2 per endpoint, at most 4n. Let's divide it between the trapezoids. How many trapezoids can you have if you generated only 4n many rays? Not more than order n. So even if you don't know Euler, you realize that it's a planar map that if you have n segments, and it has n faces, n walls, and whatever, any properties that you pick here, it will be n, order n. That's a cool idea, and it's said that I'm getting to it kind of late, but and U seems pretty beaten. But that's a highlight. So if I only have n segments and only have n walls, then the number of walls that ends in a segment, number of walls, vertical ways, that touches any one of the segments could be n in the worst case, but on average it's constant. What do I mean average? Average on what? Count how many walls hit this segment, plus how many walls hit this segment, plus how many walls pick this segment. We have n segments, divide by the walls. And since it's order n walls or n segments, the number of walls that touch an average segment is only constant. What does it mean? That if I pick a segment and remove it, how many walls needs to change? Worst case, n. We had this, here's a worst case example. If I pick a very nasty segment, average case, no matter how the bad is a scenario, average case, you're just changing linear number of walls. So how much work did you spend per how many trapezoids did you cross when you added this segment? Well, do the backward analysis trick. Let me remind you really quickly what was a backward analysis trick when we did the linear programming, where it was maybe a bit visible, or at least remind you algorithms that we nailed. I had a sequence of half planes. I had the lowermost point, and I asked, if I remove one of these half planes at random, what's the chances that I change the lowermost point? The argument was, hey, there are only two half planes that touch the lowermost point. If there is n half planes, but only two of them determine the lowermost point, if I pick one and remove it, the chance that the lower point will remove is 2 over n, because there are two of them. In 3 dimension, it was 3 over n. In d dimension, it would be d over. Same here. Pick one of the segments and remove it and correct the planar map. How many trapezoids do you have to fix if you remove it suddenly? Constant, on average. Average on what? I'll decide. How many trapezoids do I do if mentally I remove this one, or this one, or this one for each case? I remove and fix the map and put it back afterward. The chance that a trapezoid will change is only one constant over n. Let's call it 1 over n. And trapezoids, the chance that one of these trapezoids touches the segment that I just picked is 1 over n. Let's see an example. I think that it's way too in there. Let's go back to our worst case example. In my lowercase example, I had n segments that, let's say, that they are inserted first. It's not exactly random permutation. Let's say that I generated n such trapezoids. They are also continued downward. And now I just have 3 new segments called S1 and S2 and S3. If I'm inserting them in a bad order, then S1 changes n trapezoids. If I'm inserting them in bad order, I'll insert S3 first. It crosses all these green lines, which will cause all these walls to disappear, but it doesn't help S2. That also needs to cross all of them. That also helps S3. But now out of these 3, ask just among these 3, plus all this n, because I do have the n, what is the average number of trapezoids that each one of the segments touches? Remember,
They're all in, so how does a planar map looks like when they're all in? All these guys vanish. All these guys vanish, all these guys vanish. Only the vertical walls form the new segment. On every n trapezoids and segments, how many trapezoids touch each one of them? Well, one S1 is a particularly the black sheep of the segments. It touches many trapezoids, but it obscure all these small guys from S2, which in turn obscures them from even more from S3. So that's just an example that because of Euler, each segment just touches n trapezoids, meaning that if I'll remove a segment at random, it will change n trapezoids, meaning that if I'll now insert them at random and ask for each segment, if it is the last one, how many changes will it do divided by the number of segments? It will be a constant. Make sense, kind of? It's a clever argument, and it might be that the time of the day is a bit late. Think about it. That's really the highlight of why it works. OK. Just formally, what is the probability that the data structure for SI is different than the data structure of SI plus 1 when I'm doing my query point, and my query point is one of the endpoint of the segments? Just ask what is a path. Now, asking what is the length of the path or to the segments, it's just sum of random variables. And for each one of the random variables, you're asking, is a path to a query point? I'm changing the game. I'm picking my query point, and now I start adding the segments and ask, when I'm adding SI, did the path to Q changed? Is this longer or not because I'm adding SI? Well, the chance when I'm adding S1, the path to Q definitely changed. It was my first segment. When I'm adding my second segment, the chance that it changes the path to Q is only half. When I'm adding my third segment, the chance that it changing the path to Q is only 1 over 3. Changing the last one, it's 1 over n. What's the sum of all these numbers? Ln n. That's just the harmonic sum. OK. Hopefully it's synced in some level. So expected, everything here is expected. The data structure can be of quadratic size if you landed on really bad permutation, but really bad permutation will happen with probability of 1 over n factorial. N factorial is a huge number. 1 over it is very small. You have much better chance to land on a nice data structure that will create, what did we say? Every new segment add, on average, only a constant number of nodes, constant number of trapezoids, constant number of nodes. So the number of new nodes that I create by adding a segment is, on average, constant. Sum them up, the size of the data structure is only order n. And the query time, again, and I never do any balancing. It's all in the sake of the randomness. The query time, the length of the path in the data structure is only ln n, which is basically as good as I can hope. Great. What about the general assumption? So the general assumption kind of solved because I'm doing random noise. But here is a nicest trick. Said that the only case of general assumptions that I'm worried about are two segments whose left endpoints are not the same. Two segments, S1, S2, their left endpoints is not the same left endpoints, but they have the same x coordinate. And of course, if my data structure comes from any grid, it's quite likely that I'll have such segments. It's not that random noise really solves everything. If I have a few segments that all start at the same point, it's not a problem.
why are two segments that don't end in the same point? The problem is that now I have trapezoids that have multiple neighbors on my right side. I use the fact that I have only two neighbors on the right side, so when I'm tracking one of the segments, I can easily see, oh, you're exiting trapezoid 1. Are you going too much talking? You're exiting. I need the two trapezoids because as I'm traveling along SI, and I realize that I just left trapezoid A, then I need to check, am I in B or am I in C? But since I have only two neighbors on my right side, it's very easy to check, are you to which one of the two neighbors you are. If I have many neighbors on the right side, then it's not obvious. So here is a cute trick. You add the random noise, but it's not random noise for each point. What are you doing instead? You're taking every point, x, y, take x, y, and transform it into the point x plus epsilon y and y. Epsilon is some very tiny value. What did I do by doing so? Two endpoints that had the same x, now they are all shifted to the right. That's a shear transformation. What does shear transformation do? It takes in the xy a rectangle, and it moves it into a parallelogram. I'm exaggerating it. It's a parallelogram. These, the two horizontal edges stay the same. I'm not drawing it well. That's my source, and that will be the new, where the points from here are going to. It's not rotation. Make sense? And if I'm picking epsilon at random, there is only of point, a great chance to land on a tiny epsilon that doesn't change anything. It doesn't change what are the trapezoids, what's the map, etc., etc. It just makes sure that I'm getting rid of this degenerate. And it's much more practical than adding random noise. Next topic. I think easier to digest. Especially when you don't see it, it's easier to digest. The reason of why I'm not talking about the midterm is the same as Tuesday. It was not entirely planned, but there are still people that didn't take the midterm. Surprise, surprise, but for good reasons. Didn't expect it to take that long, but yeah. So, hello. Voilà. So when we have computer game, it has objects. Every object is triangle or a quad, and they are opaque. And I want to render, and you told me where is the viewer. The viewer is also a location. You actually want to tell me where is the camera direction, even though I don't need it for this particular algorithm, and what various other parameters, but essentially to give you a feeling that you are not playing 1970s computer games, but there is actually 3D scene behind it, you need to say there is object lives in 3D. And as in 3D, if they are all opaque, nothing is transparent, there are surfaces or items that you need to remove. If this cube is opaque, you don't see the back side of the cube. And that's one of the big hints to give you the 3D feelings of the scene, obviously. It's not the only way to generate the feeling of 3D. You will, of course, use a perspective, things that are further in than you are smaller. You'll use shading, which side the light is hitting it. You will use shadows, well, like you have source of light and it casts shadows, but hidden surface removal will be one of them. So babysit Zoom. And OK, so how do we are input set of triangles and the viewer location, and I want to ask which items to remove, which surfaces to remove. Right? Otherwise, you will not have any depth perspective of how this cube actually looks and if it's convex or concave and so on. So what should be the practical answer? Practical answer would be it's hopeless to do it in a single CPU. I mean, fine, you can do it for one particular scene. If it's nothing interactive and you have enough time, then one single core CPU can handle it. If you have multiple, if you are trying to do anything that refresh in any reasonable way, then it's pretty much hopeless to do with one CPU. And so you need GPUs. So the ultimate answer is just use GPU and the problem solved by it. Not exactly. I stole some slides here from my graphics course. That's a scene with 15 polygons, surfaces, not too bad. More surfaces. More surfaces. More surfaces, 3 million polygon in this case. Still, we are not talking about shading and shadows, of course, just about what are the objects behind this gentleman that you don't see. And many more polygons, many more triangles over here, at which point your GPU is also has issues. Even if you are upgrading and so on, you still have issues. So for really large scenes, it's not enough. Right? Your GPU is not the ultimate answer. GPU is still very important, but it's not the ultimate answer. And there are plenty of ultimate answers, of course, but one of them will say, here is my viewer, and I want to find what are the objects that are close to my viewer, and what are the objects that are in the background, and treat each one separately. Right. I'll render each piece separately, but in particular, I'll see that this building that you see over here occludes quite a large area of the background that I don't need to render. Okay. Same example over here. Here, look at the background and look at the foreground. Now, let's look for a moment at the background and ask, what do I do with, how do I use the binary space partition, BSP? It's a big class of trees that are the binary space partition that essentially says, take the whole 3D space, split it, hopefully by something simple like a plane. This plane doesn't have to be, and sometimes really don't want to be, orthogonal to the x and y or z. Sometimes it is, sometimes it isn't, depending on what exactly the options. And now you have smaller regions and keep splitting them. So we have seen BSPs before. We have seen KD tree, it worked for points, and the splitting was always orthogonal. We have seen quad trees. Well, quad trees are not really BSPs of 3Ds, are BSPs of 2Ds. In 3D, they are called octrees. Same structure, just in 3D. Then you're splitting a region by 1. So you have one region, split it by x, 2 regions, split it also by y. Each one splits to 2, and split it also by z. So now it's oct from 8, 3. But there is plenty of other BSPs, and they are very nice. So here is, that's unrelated to our topic, but here is a very, very useful and clever idea how to work with what is in the background. What is in the background if you are moving your head a bit or moving a bit? What is in the background far away from you doesn't change that dramatically. So even if it's very complicated wolf, I can prepare the wolf in certain number of directions and somehow interpolate between this direction depending on where the user is. And these are just static images that I can use as texture, as a way for the background, use it as a billboard or imposer. That's what I see in the background. Now, the wolf is, of course, not really convex. It's not a rectangle wolf. And I can see through the wolf some pieces of the grass underneath the wolf, but that's because I set the alpha, the transparency of the pixels between the wolves, to be completely transparent, so it doesn't occlude what you have behind. So that's a quick glance into billboarding. Inside the wolf, now, back to how do I do image removal, the painter algorithm will be a very, very simple and sometimes extremely efficient algorithm to render it in 3D. And it will say, oh, you want to render this scene? Start rendering it. Forget about surface removal. Just render it, but make sure that you render the most remote object, this hill. On this hill, what is a bit closer to you? The house is a bit closer. Then render the house. Now render the tree. Why? It's closer to you. But when you're rendering the tree, you are changing the colors of some of the pixels that were originally whites and greens and whites and to whatever brownish. And finally, render the closest things to you. So that's a painter algorithm, and we are going to see what to do, how to build an efficient BSP that in turn will lead to efficient painter algorithm as one of the many, many applications of BSPs. Thank you. And